Hello everyone. We are discussing composite function. Our composite function is, so let me go through one more time. So we have a f composite g function, okay, with a domain x, and this f composite g function is equals to f of g of x. Okay, so this is our composite function. We started the very first example and we did part A. Okay, in part A we are asked to find the f composite g and we are asked to find the domain for the f composite g. So our f composite g function is 4s square plus 1. This is the quadratic function and we can choose any number for s as our input. So all real number is a domain for this function. Now let's go ahead and do number B. In number B, we are asked to find the expression for g composite f of s and write the domain for g composite f. Okay, so we need to find what is g composite f of s. So we have g composite f of s, and its definition is we have a g of f of s. So this is the definition. Now we go ahead and substitute our f function. So we have g as it is in our definition, and this f of s, we know this is the output, and we know this expression g of f of s is equals to s squared plus 1. So let's go ahead and substitute f of s. For f of s, substitute s squared plus 1. So this is our f of s. Okay, now we need to find g of s squared plus 1. So in this case, our input is s squared plus 1 for g function, and we want to know what is the output when your input is s squared plus 1 for a function g. Okay, so our function g is, so if we go back here, our function g is negative 2s. So let's go ahead and substitute s squared plus 1 for every s in our g function. So in the g function we have negative, okay, and we have 2, and for s we're gonna substitute s squared plus 1. So we have s squared plus 1. Now here in between negative 2 and s squared plus 1 we have a product, so we distribute negative 2, you distribute negative 2 for s squared, and you distribute negative 2 for 1. And we have negative 2 s squared plus 1, and this is our g composite f function. Okay, so this is the expression for g composite f. And the next here we also need to find what is the domain for this g composite f function. Okay, finding domain means we want to know what kind of number we can choose for our domain. Our domain is s here, so we want to know what kind of number we can choose for this s so that we get the real output. Okay, so this is here quadratic function. Okay, and if we have a quadratic function, we can choose any number. Okay, it does not matter what number you choose. For s from negative infinity to positive infinity, we always get a real number. So the domain for g composite f function is all real number, or we can write negative infinity to positive infinity. Okay, so this is for part B. Now let's go ahead and see what do we have for part C. So in part C, we need to evaluate what is f composite g of negative 1. So in part C, we need to find f composite g of negative 1. So here in this expression, negative 1 is the input. Okay, now what is this in? Now we have this input negative 1. Now is this the input for f function, g function, or for what function? So here we can see the function f composite g. So this is the function, okay, so this is the name of function. This is one function, which is the f composite g. So we have this f composite g function, and we have the input -1, okay, and we are asked to find f composite g of -1. It means we want to know the output, okay, of this -1 for our function f composite g. So at first, let's write what is f composite g equals to. So our f composite g of s. So we know what is this what is the function f composite g. So if we go back to our number b, okay, not number b, number a. So in number a, we did calculate what is f composite g. And so our f composite g here, our f composite g is 4s squared plus 1. So our f composite g is 4s squared plus 1. Okay, now this is the function, this is the output when your input is s. But we have given our input as a -1, and we want to know what is the output when your input is -1. So what we're going to do here is that we're going to substitute -1 for every s in our f composite g function. So we have f composite g, okay, for s we have -1 equals, we have 4 times our s is -1 squared plus 1. Now let's go ahead and simplify this. So we have 4 times -1 squared, that is +1 plus 1. So this is 4 times 1, 4 plus 1, which is equals to 5. So whenever your input is -1 for this f composite g function, we get the output 5, which is a real number. So -1 is a domain. Okay, we know f composite g has a domain all real numbers. Okay, now let's go to the next one. In number D, we need to find g composite f of -1. So for number D, we want to find g composite f of -1. So we need to find here the output, okay, when your input is -1. Now what is the function here? Our function is g composite f. In number C, our function was f composite g, okay, and we had g composite f. So here these two are a different function. And from part B, we know what is g composite f. So from part B, our g composite f, okay, this g composite of f is -2s squared plus 1. So let's write that function. So g composite f of s is, so one more time, so this is -2s squared plus 1, -2s squared plus 1, and we want to find g composite f of -1. Okay, it means we want to know the output when your input is -1. So in this function, our input is s and our output is -2s squared plus 1. Now let's see what happens if our input is -1. So you substitute -1 for every s. So you have -2 times -1 squared plus 1, and this is -2 times -1 squared is +1 plus 1. -2 times 1, -2 plus 1, and we have -1. So this is the output. Okay, so this is the output, -1 when your input is -1 for this g composite f function. Okay, this is all for our very first example. Now let's go to our next example. So here in the next example, we have our function f of x equals to 1 over x, and our g of x is x squared minus 1. And we are asked to find f composite g and its domain, g composite f and its domain. Okay, let's go ahead. So let's start from number A. Okay, our function f of x is 1 over x. Our g of x function is x squared minus 1. And let's find f composite g function, and its input gonna be same as f and g, which is x. Okay, so from the definition, its definition is we have f then of g of x. So this is the definition. Now let's go ahead and substitute our g of x. So we have f as it is, and for this g of x, we're gonna substitute x squared minus 1. So we have x square minus 1. Okay, so we have f of x square minus 1. So we are asked to find the output when your input is x square minus 1 for the function f. Okay, and we know our f function is 1 over x. So we substitute x square minus 1 for every x in our f function. So we have 1 in the numerator over, so for this x we're gonna substitute our input x square minus 1. So we have x square minus 1. So this is our f composite g of x function. Okay, and the next we are asked to find the domain for this function, for this f composite g. Now this function is a rational function. Okay, so rational, we have the denominator, and whenever we have the denominator and when we are looking for the domain, we want to get rid of 0. We don't want 0 in the denominator. Okay, so finding domain means we want to find the numbers, okay, for x such that as our input, such that we get the real output. Now in this expression, if we choose x equals to positive 1 and x equals to negative 1, our output is undefined. Okay, like for example, if you choose x equals to 1 as your input, then f composite g of 1 is equals to, we have 1 over, you substitute 1 for every x, we have 1 square minus 1, and this is 1 over 1 minus 1, 0, and this is undefined. Okay, this is undefined, so this is not a real number. So what we can say about 1 is not a domain for f composite g. But here we want to know all possible inputs, all possible numbers for x, such that we get the real output. Okay, now this is the rational function, and for rational function, every number that make denominator equals to 0 are not the domain, but other number are the domain. So in this expression, if we choose our x equals to 1 or x equals to negative 1, we get 0 in the denominator. So these two, negative 1 and positive 1, are not the domain, but every other real number are the domain. So let's write this domain in the interval notation. So to write in the interval notation, we draw a number line. We have negative infinity to positive infinity. So our numbers which are not the domain are negative 1, positive 1. So these two are not the domain. Okay, but every other number are the domain. So we are excluding these numbers from our domain set. So excluding means we're going to use an open circle at negative 1, and we're going to use an open circle at a positive 1. Now let's write interval notation for each of these part of the number line. So for the first part, we have negative infinity to negative 1. Since we have open circle, we're going to have the parenthesis. Second part is from negative 1 to positive 1. Both of these are not the domain, but every number in between these two numbers are the domain. So we are excluding means we're going to use parenthesis. And the last part of this interval is 1 to positive infinity. 1 is not the domain, so we have parenthesis. Okay, now we have these three set. Okay, so we can have a number from our first set or second set or a third set as a domain. So the domain for this function, okay, so the domain for our f composite g function is negative infinity to negative 1 union negative 1 to positive 1 union 1 to positive infinity. So here every real number other than negative 1 and positive 1 are the domain for this f composite g function. Okay, now let's go to our number b. In number b, we need to find g composite f and its domain. Okay, so we need to find g composite f for number b and its domain. Okay, so let me rewrite our g of x is given as, so g of x is x square minus 1. Okay, and our f of x is equals to 1 over x. Now we are actually find f composite g. Okay, sorry, g composite f. So here g composite f of a x Its definition is we write g function at first, then of, then the other function f of x. So we make a substitution of f of x. Okay, so our f of x, so this is f of x, and we know what is f of x. F of x is 1 over x. So let's go ahead and substitute. We have g as it is. Our f of x is 1 over x. Now let's find what is g of 1 over x. So here 1 over x is the input for our g function. So we substitute 1 over x for every x in our g function. So this gives us, we have x square, and for the x we're gonna substitute 1 over x. Okay, now we have square negative 1. Okay, now let's simplify this. So we have the numerator and denominator is square, so this square is for numerator as well as denominator. So 1 square is 1, x square is x square negative 1. Okay, now this is our g composite f function. Okay, so here this is the expression for the g composite f function, and the next we need to find its domain. So in this function we have the rational expression. Our rational expression is 1 over x square. So if we have the rational expression, we always try to exclude a number that makes denominator equals to 0 from its domain. Okay, so what numbers make a denominator equals to 0? It's the 0, right? So if we choose x equals to 0 in this expression, if we choose x equals to 0 in this expression, we get undefined output. We do not get the real output. So 0 is not the domain, but every other number is the domain for this function. So let's draw a number line. So we have negative infinity, positive infinity, and 0 is not the domain. So we have open circle, and let's write down the interval notation for each part of this number line. So we have negative infinity to 0. 0 is not the domain, so we are excluding. Excluding means we're going to use parenthesis, and the second part is from 0 to positive infinity. Okay, so our domain for g composite f is from negative infinity to 0 union 0 to positive infinity. So these are the domain for g composite f function. Okay, so this is about our f composite. This is about our composite functions. Okay, now we do have a real life application here. Okay, so let's go to this next example. So in the next example, we have the cost of a fuel, okay, for a running of fleet of vehicles owned by a global X corporation is given by. So we have this cost function, okay, c of x is equals to 2.5x. This is the cost function, and here our x is the domain. Okay, so here our c is the function. Okay, so c is the cost function, our x is the domain, okay, which is the input, and our output is given by 2.5 times the input, 2.5 times x. Okay, now what is x here? Our x is the total number of gallons of fuels used. Okay, so x is the total number of gallons of fuel used, and the cost is given by 2.5x. Now the Canadian branch, however, records its fuel consumption in liters. Okay, so the brands, they record the fuel consumption in liters, but we are given here the cost. Okay, so we are given the cost of fuel, and our x is the total number of gallons of fuel. Okay, but the Canadian brands, they records the fuel in liters. Okay, the conversion from liters to gallon is given by g function. Okay, so we have this g function, and this g function help us to convert from liters to gallon, and x is the liter. Okay, so x is the number of liters, and we get our gallon as a 0.26x, which give us the gallons of a fuel from liter. It means it converts liters to gallons. Now we are asked to find c composite g of x. Okay, now let's go ahead and find this a. So in number a, we are asked to find c composite g of x. So from the definition, so we have c function of g of x. Now we substitute our g of x. We know what is g of x. So we have C as it is. G of x is 0.26x. Okay, now the next we find C of 0.26x. It means C is the cost function. So we're gonna find the cost of a fuel when your input is 0.26x. And for this we use our cost function, and cost function is given by this expression here. So we substitute 0.26x for every x in our C function. So we have 2.5 as it is. For x we're gonna substitute this input, which is 0.26x. okay, so now let's find what is 2.5 times 0.26. okay, so let me go ahead and multiply. So when we multiply 2.5 and 0.26 we get 0.65. so we have 0.65x. so this is C composite G function. okay, now what it means for us, so it tells us to interpret here. okay, so it tells us to interpret here. Now let me draw a mapping diagram here. So let's say we have a G function. So we have a G function. okay, so we have this G function. So this is the G function from first set to second set, which convert liters to gallon. okay, and we have a cost function here. So this is our cost function. okay, so let's say we have x number of liter, and this x number of liter, okay, is converted into gallons by G function. okay, so when our input, which is the x number of liter, okay, this x number of liter is converted by gallons with the help of G function, and that is G of x. okay, now this is our number of gallons of a fuel. okay, so we had a x liter, this G converted x liter into a number of gallons. okay, now we have a number of gallon, and when we have a number of gallon, cost function, it helps us to find the cost of a fuel. okay, so we have C of this input is G of x. okay, so we have C of G of x. so this is the cost. okay, and here we have this function. This function is our C composite G function. okay, so here our C composite G, so we know what is this. So C composite G, this is 0.65x. so this function, for this function, the input is x. okay, this input is x and the output is this expression, and our input x is the number of fuel in liters. okay, so x is the number of fuels in liters. Now so C composite G function give us the cost of a fuel. okay, and where this x, okay, this x is the number of fuels in liters. okay, so when we are given a number of liter, we're gonna use this function. okay, we can't use this C function. okay, if we want to find the cost. The reason is that this function is used when your x is number of gallons. okay, but this function, this C composite G function, we can use this composite function when our x, okay, when our input is liter, then we use composite function. okay, so this C composite G function give us the cost of a fuel. okay, and where our x is the number of liters. okay, now in part B we need to find the cost of 120 liters of fuel. okay, so we have the two functions to use to find the cost. The very first function is C of x. So C of x, but in order to use this C of x function, our x, the number of the fuel has to be in gallons, okay, but our fuel is in liters, so we're gonna use C composite G. So here we are asked to find for number B. So for number B, we are asked to find C composite G of our X. This X is the liter, okay, and we need to find the cost of 120 liter of fuel. So our input is 120 and our function is C composite G. So let's write down what is C composite G. So C composite G function is given by 0.65x. So we want to know C composite G of 120. So when your input is 120, you want to know what is the cost. So you substitute 120 for every x in your C composite G function. So we have 0.65 as it is times 120 for x, which is the input. Now let's see what we get here. So here we have 0.65 times 120 and we get 78. So the cost is 78. Okay, so we have 78. Now let's go back. What is the cost? Okay, now it does not tell us the cost is in dollars or okay. Now the cost is here. Okay, let's say we have 78. Okay, should be $1. $78 for 120. Yeah. So this is the $78 is the cost for 120 liters. Okay, so this is for this real life application. Now the last example for this section is, so we need to find this expression. And now we have seen this expression, right? This is the difference quotient. So we need to find the difference quotient when our f of x is 2x squared plus 1. Okay, so to find the difference quotient, so what we need to find? We need to find what is f of x plus h. Okay, f of x is given to us, which is 2x squared plus 1. Okay, so let's go ahead and find f of x plus h. So our f of x is 2x squared plus 1. And we want to find what is f of x plus h. So we want to know what is the output when your input is x plus h. So you substitute x plus h for every x on your f function. So we have 2 as it is. For x, we're going to have x plus h. We have square as it is plus 1. Now let's go ahead and simplify this. We have 2 x plus h square is same as x plus h times x plus h plus 1. Now we use the FOIL. So you multiply inside term, you multiply outside term. Sorry, you multiply, this is the first term, you multiply the outside term, inside term, and the last term. Oh, I messed up here. So let me go one more time here. So so we have 2 as it is. Okay, so we have 2 as it is. Now we multiply the first term, x times x. So we're gonna get more than 2 terms, so we're gonna use parentheses, x times x squared. We're going to multiply outside terms. Okay, so our outside terms is x and h, x times h, that is xh. Then we multiply inside terms, h times x, so which is hx or xh, and we multiply last terms, which is h times h, so which is h squared plus 1. Okay, now we have the product here, we distribute 2, so we have 2x squared plus 2xh plus 2xh plus 2h squared plus 1. So we do have a like terms here, 2xh, so let's add these two and we get 2x squared plus 4xh plus 2h squared plus 1. So this is our f of x plus h. Now let's substitute our f of x plus h and f of x in our difference quotient expression. Okay, so our difference quotient expression is f of x plus h minus f of x divided by h. Now let's substitute our f of x plus h, which is 2x squared plus 4xh plus 2h squared plus 1. then we have negative f of x. Our f of x is 2x squared plus 1. We do have two terms, so make sure you have the parenthesis 2x squared plus 1 divided by h. Now let's get rid of parenthesis. You distribute negative, so we have 2x squared plus 4xh plus 2h squared plus 1, negative times positive 2x squared, negative 2x squared, negative times positive 1, negative 1 divided by h. Now let's look for the like terms. 2x squared, positive and negative cancel, positive 1, negative 1 cancel, which is 0. So the remaining, we have 4xh plus 2h squared divided by h. We have the h as a common factor, so let's factor out. So we have 4x plus 2h divided by h. So here we have the factor. Okay, we have the two factors in the numerator. Okay, and if